So we are continuing from where we stopped the other time, lecture 5, trying to calculate bending moment on this beam AB. We have been able to get the reaction A and reaction B. We find that it is equal to 3, each of them is 3 kilonewtons. So to get the bending moment at C, as I earlier explained, I put the moment at C. Assume it to be looking at A where I started. I say it's positive. I can call it negative if I like. It automatically. The only thing that if I call it negative, any moment that is against it becomes positive. It's as simple as that. So I now call it positive. MC turning like this. Call it. So the next moment that from A to where, because we started from A to C now where we are, the next moment will be moment caused by force of reaction A, which is reaction A times that distance. So, and it's against MC, so it will be negative minus 3.5 RA. There's no other moment because the force 6 will not give a moment because it is the point we are talking about, that point at point C where 6 is acting. So it will not generate moment there because its distance from itself is 0. Its distance from itself is 0. Distance of reaction A from C is 3.5. That's why we have 3.5 here. But distance of 6 kilonewtons from that point C is 0. That's why we're not bringing that. So there's no another force because just like I said earlier, trying to get bending moment is converting forces to moment. So there's no other force from A to C. So and that means for this point C, the moment at that point to be equal to 0, that point to be in equilibrium, when they'll be equal to 0. So it's equal to 0. So that means I have that MC is equal to 3.5 RA. And we know RA to be 3. That's times 3, which is equal to 10.5 kilonewton. MC is equal to 10.5 kilonewton. So I can get a moment at NB will give me 0. If I take moment at NB, it will be a mark B. If I take it looking at where I started, if I call it positive. If I call it positive at MB, I will have a moment at B, if I call it positive. Then RA will be against it. That will be minus 7 RA. Like this. So the 6 will be in the same direction. So it will be plus 6 times 3.5. For the point at B to be 0, to be in equilibrium, so it's equal to 0. So MB will be equal to 7 times 10.5 minus 6 times 3.5. So that will give 0. That is RA. Sorry, RA is 3. RA is 3, not 10.5. RA is 3. That means 7 times 3 minus 6 times 3.5 gives 0. So that is that. So that's the bending moment. If I want to draw the diagram of the bending moment, I have, this is the beam. At point A, the bending moment is 0. At point C, the bending moment is 10.5. At point B, the bending moment is 0. And here, the bending moment diagram is a graph of bending moment against distance. A graph of bending moment against distance. So in this case, you will see that in that graph, from the way the bending moment diagram equation looks, that graph is a straight line graph. A straight line graph having only a distance, not where distance is the power 2. That will be quadratic. This time is a straight line graph, so I can easily plot. From the moment here is 0, the moment here is 10.5. So if I join, and the moment here is also 0, so this is 10.5 kilonewton, the moment. This bending moment diagram is positive if you look at the bending moment values. Now the next thing I should get is the shear force. The shear force at every point is the summation of algebraic summation, or algebraic summation of the total force at that point, from where we started from point A, moving this way. That is the algebraic summation of the forces. If you come to at point A, algebraically, the force there, if I try to call it positive, is RA, which is equal to 3 kilonewtons. RA is equal to 3 kilonewtons. So the shear force at point A is 3 kilonewtons. The shear force at point C is 3 kilonewtons. 3 kilonewtons and against 6 kilonewtons. So if 3 kilonewtons is taken to positive, pointing up, then 6 that is pointing down will be negative. So it becomes 3 positive minus 6, which is 3 kilonewtons. So it continued on getting to B. This 3 here minus 3, that on getting to B, it makes reaction B, which is 3. That means minus 3 plus 3, because reaction B is pointing up, which gives you 0. It closes at 0. So the bending moment, the shear force diagram will be this way. Now, this is the structure. From here, we have a value. The value 3 kilonewtons. That's reaction A. It continued. When it gets to the middle, we are 6 at point C. At point C, 6, 3. This 3 minus 6 that is against it, it comes down to minus 3, because this place is positive. It comes down to minus 3. So now that minus 3 continued. There's no other force until when it gets to the reaction. When it gets to reaction B is 3. So that minus 3 plus 3, because reaction B is up, it closes here at 0. So this is negative, this is positive, this is 3 kilonewtons. So that is the shear force. This is shear force diagram, bending moment diagram of this beam. So with this value now of bending moment and shear force of this beam, if one wants to design this beam, one will be able to design the beam, because one has gotten the stresses in the beam. That is the bending moment. We get the one at the center. We can get anywhere we want, even at any point on the beam. We get the same way. We get a bending moment. But we wanted to take the one at point C to get a maximum. And we've gotten, if we are designing, we use 10.5 kilonewton as the bending moment to design the beam, and the shear force of 3 kilonewtons to design the beam. Whether you are designing the beam is steel, or is concrete, or is plastic, or is timber, the value of the stresses does not matter. Whatever material, every material will be able to design the beam. We'll get to that. So that is with regard to solving this beam. Thank you. We're going to the next beam.